Hey everyone, my name is Vijay. I'm going to show you how to solve problem 4 of test 2. Now, problem 4 gives us a circuit with a thin wire and which carries a conventional current I in the direction shown by the arrow right over here. Look, it's going this way, and it gives us three parts. One is to determine the direction of the magnetic field. The second one to set up the formula for the magnetic field. So basically, in this case, it will be the integral. And finally, it asks us to determine the magnetic field at the observation location, L plus T, 0, and 0. Now for the first part, it's very simple. You just have to use the right-hand rule. The right-hand rule says that if you point your thumb in the direction of the conventional current, so this way, your fingers will curl towards the magnetic field. So in this case, it's curling out of the page. So for this one, for the first part, the direction is out of the page via the right hand rule. Okay. Then the next is to set up a formula for the magnetic field. Now that is we are given a formula sheet. So in that formula sheet we get the formula that dB is equal to mu naught over 4 pi I dl by r hat cross r hat over the magnitude of r to the 3/2. And so to get this, 1 second. So looking at this, we can find what r is. R is just, so we can find r, which is the distance of the observation location, which is P. We're trying to find the magnetic field at P, this area. So that is, first we have to define a DL. I'm going to define DL halfway through this wire, so just for it to be easy. So around this area right here, DL. So for that, I'm going to say R is equal to L plus D minus DL, because this is also, if this half is DL, this half is also DL. Sorry, no, yeah, minus DL minus H, because P is located right here below the wire, minus H, and 0. Sorry, I squeezed that in right here. And so from there we can find DL, which is just equal to the DL that we defined in the negative x direction, since current is in the negative x direction. Now, r hat, that's going to be a bit tougher. We get at equal to L plus D minus L minus H 0 all over square root of L plus D minus all squared plus minus H squared. Now r hat is going to simplify to, that's r hat itself. And so what we have to do is we have to apply this formula, or apply these constants, into this one. So we get dB equal to mu naught over 4 pi, which is a constant, I h dl all over r hat, which is all over r, sorry. So L plus D minus L squared plus H squared, all to the, all of that to the 3 halves. And of course it's going to be, since the magnetic field is pointing out, it's going to be in the negative z direction. I mean positive z direction. And so what we do that is, with that is, we set up an integral right here, so that we can find the actual magnetic. This is just the derivative of the magnetic field. To find the actual magnetic field, we gotta find the antiderivative. So that would equal integral from 0 to the distance, which is L, mu naught over 4 pi, I h dl over L plus H plus, L plus D plus L, slow L squared plus 8 squared, all of which is then raised to the 3 halves. And of course, once again, multiply by 0, 0, 1. So that's the final integral to find b. Now we don't really need to solve this out, but I don't think it matters right now. There it is. Final integral. Now for the last part, determine the magnetic field at an observation location L plus D 0, 0. Now we know for a fact that since dl is in the negative x direction and observation location, which is just r, is also in the negative x direction, I mean the positive x direction, so they're both in the x direction, that the cross product of L plus D plus R, L plus D and R hat would just give us 0, 0, 0. So it's positive, so I mean it's parallel, so we will get 0. So our magnetic field will equal 0. And we can do this the longer way where we solve out the integral, but through conceptually we find out that the magnetic field is 0. Because since both of these are in the x direction, the cross product of dl by r hat will give us just 0. And since 0 is on the numerator, our final magnetic field is also 0. So it's very simple. And